So yeah, I will present you my a part of my PhD thesis and about mantle inheritance and mantle-melt interactions and lithospheric breakup. And this work is already published in an EPSL article. So yeah, just to give an introduction, here you have really the state with a lithospheric subcontinental mantle and crest, and going to ocean seafloor spreading. And in the same way that inherited structures are critical for rift nucleation in magma pro-extensional settings, inheritance is essential to understanding the breakup and previous stages. And I investigate the influence of the petrological inheritance of the mantle on the development of magma pore rifted passive margins. And as you can see here, spatial and temporal evolution of the subcontinental lithospheric mantle from rifting to seafloor spreading show a direct link between the different temporal stages and the evolution of the subcontinental lithospheric mantle along cross-section of the evolving rifted margin. So the passive margin is really a tape recorder of the stages. And all past studies on the mantle rocks and mantle melt reaction allow to develop this really generic model of a hyper-extended magma pore rifted margin. This model is really not perfect, but it gives you really a generic view of what you can find is this type of rifted margins. And as you can see here, the lithospheric mantle can be divided in three sections, so-called the mantle type 1, who corresponds to the inherited subcontinental mantle. And then you have, as here, the type 1. Then you have here the type 2, which corresponds to a subcontinental mantle that has underground revitalization by melt percolation and entrapment. And then here, the mantle type 3, that corresponds to the depleted mantle after Morbius extraction and the formation to the steady state spreading center. But this generic model will be made here with. So here you have the magma pore rifted margins, all the magma pore rifted margins in the world, and you in blue. And this generic model I already present you is really made with three passive margin, Newfoundland, Western Tethys, and Iberian margin. So really Tethyan margin and located in a small area. And I then wanted to go here in the Diamantine zone, so in Southwest Australia, to test really this model and to show if it's possible to correlate the processes or if it's wrong. So here you have Australia and the Diamantine zone where dredged samples, and as you can see here with the map on the right, you have really an older subcontinental mantle with probably more Proterozoic mantle, so really older than the Tethyan mantle. And here on the Diamantine zone, you have effectively periodatites, a lot of periodatites. And these periodatites were dredged by four dredge points. And in these four dredge points, you have periodatites. But you have not just one type of periodatites, but two petrographical different types, with here on the left side this periodatites with cladopyroxenes and spinels, so spinel lesolites. And on the right, you have other periodatites with clinopyroxenes and orthopyroxene, but also plagioclase and spinel. So we call it plagioclase lesellite. And as you can see in the model, this could be two types of mantle, because you have really spinel lesellite who is in more depth, and plagioclase lesellite is normally in shallow depth. So I make here one map with a chemical cartography from a plagioclase lesellite. And as you can see here, the petrography is really complicated because it's not normal for a periodotite. You really have olivine, orthopyroxene, clinopyroxene, but also plagioclase, who is really embedded with the clinopyroxenes. So really particular textures. And here I will go a little bit more precise in the textural observation. So that's our on plagioclase lessellites, because spinel lessellites are really not well preserved. So I show you here really a particular texture only in plagioclase lessellites. And here on the first picture, you can see clinopyroxene with a texture with you can see inside the clinopyroxene, orthopyroxene with plagioclase, really inside the mineral. And on the bottom, you can see that plagioclase and orthopyroxenes are sometimes really around the clinopyroxenes. And these clinopyroxenes are really different from this one. We call it clinopyroxene 2, so neoblasts, where this one are called porphyroclasts. So first stage of clinopyroxene, and here second stage of clinopyroxene. And the second stage of clinopyroxene are really most with plagioclase. And in the same rocks, you can find this type of structure, plagioclase with olivine together, in this in the surrounded from orthopyroxene with a holly leaf texture. So really orthopyroxenes they are like grabbed from the plagioclase and olivine. And in the same rocks, you can find almost spinel. Spinel are normally in a deeper than plagioclase, but here spinel are in these rocks. And you can find two types of spinel, really spinel like the black spinels and really brown spinels, but the brown spinels are only in orthopyroxene embedded. So really a lot of textures. And when we show the geochemistry, you can see this one. So here you have really a mineralogical diversity. In red, you have the plagioclase lesellite, and in green, the spinel lesellite. And this mineralogical diversity is observed in a geochemical point of view, with evidence of partial melting on the one hand, and evidence of exchanges between magmatic fluid and periodite on the other. Because as you can see here for the spinel lesellites, so in green, have a low chrome number and titanium content with higher Mg number, while plagioclase lesellites show really a higher content of titanium with higher chrome number and lower Mg number. And titanium is really known as a proxy of exchanges between the rock and melts. So this is really the sign that you had a melt in these rocks as a plagioclase lesellite who go into the rocks and make exchanges with the minerals in the periodotite.
You're now at 10 minutes.
Yeah. And in this plagioclase lesellite, we show that we have two types of spinel, black spinel and brown spinel. The brown spinel, you can see here, it's the spinel in orthopyroxenes, OPX. They show really the same geochemistry than spinel in the spinel lazulite. So really, we call this also as missing link between the spinel domain and the plagioclase domain, as you had spinel lazulite who go in the plagioclase domain and had in the first stage the same geochemistry, but then if you have melt who goes into these rocks and make exchanges, you make a different geochemistry from these minerals. But if you preserve the minerals in another, like the spinel and the orthopyroxene, you can have the first stage geochemistry. And so really a link between the two mantle types. And if you go to the Klein-Opthersen geochemistry, as you can see here, sodium and Mg number are really different in spinel lazulite and plagioclase lazulite, with really high sodium content in spinel lazulite, as you can see in all subcontinental lithospheric mantle for Klein-Opthersen in periodatites, but lower sodium in plagioclase lazulite, who shows really that you had a partial melting stage. In aluminium, you can see here that it's not so different, but if we make a difference between neoblasts and porphyroclasts, you can see here that it's really different, with a higher aluminium content in porphyroclasts core, only core, because in plagioclase you have the porphyroclasts and the melt was going in these rocks, so only the cores are preserved from these exchanges. But the rim from the porphyroclast and the neoblasts show really the same aluminium content and show that you have really exchanges with the melt. So two generations of Klein-Opthersen with distinct texture and geochemical composition. And here I will show you then the three stages in these rocks, with one reactive process flow with the orthopyroxene that I replaced by plagioclase and olivine. Then impregnation, the Klein-Opthersen I replaced with a mix between plagioclase and orthopyroxene. But here we have also a third stage, a third stage here with the formation of Klein-Opthersen neoblasts, so a second time in Klein-Opthersen, and this is called refertilization. So in a third stage, I wanted to modelize this one to give more precision. And here you can see neodymium versus sodium. Why I chose these elements? Because they have not the same compatibility at low and high depth. At low depth, sodium and neodymium have really the same CAD, so compatibility, but at higher depth, sodium has a higher CAD than neodymium. And that's why when you have the lazulite in a garnet field, you don't have the same compatibility than in a spinel or plagioclase field. And so in here, you can see two stars, blue stars and a violet star. The blue star is a Klein-Opthersen in the garnet field, when the violet star is a lazulite in a spinel field, so not so high depth. And I take a Klein-Opthersen and I make partial melting in the rock. And you can see here that the content in sodium and neodymium is decreasing, but not in the same way if you are in the garnet field or in the spinel stability field. And here you can see that the spinel lazulite have really, the model fit really with the spinel lazulite data. And that show here that we have between 3 and 10% of partial melting First one in the garnet stability field, and then in a plagioclase in the spinel stability field. But this do not fit with the plagioclase lasolite data from the clinopyroxene. That's why I made a second stages of this model. I took peridotite who made 4% partial melting in the garnet stability field, and then goes in the spinel stability field and was already 4% partial melting in the spinel stability field, and then goes in the plagioclase stability field. So really from higher depth to shallow depth, and then under a mantle melt interaction in this plagioclase lasolite field. And as you can see here, is that this fits to the data, but you have two curves, and these two curves are different because when you go from the spinel stability field to the plagioclase stability field, the spinel is not stable. So one part of the spinel goes to change in plagioclase, but as you can see in the plagioclase lasolite we have here, not all the spinel stability, not all the spinel is going to make plagioclase. So the dark red star is when 50% of spinel goes in plagioclase, when the not so dark red star is when all the spinel goes to plagioclase. And here you can really see that the model fits the data and show 4 to 5% maximal mantle melt interaction. And so that's the end of my presentation with some highlights. I trying to show you that yes, the subcontinental mantle is here inherited and sometimes impregnated, which records really the first stages of oceanization. And the diamantina zone show common mantle domains and processes to Tethyan zones, regardless of the inheritance. Thank you.
Thank you, Melanie. That was great. We don't have a lot of time for questions. If somebody has got a quick question, they could put their hand up and I will see it, or put it in the chat. In the short term, I'm just curious, in terms of that older inheritance that you think is built in there. So what is the source of that inheritance?
In the diamantina zone.
Yeah, I'm not. This is not my area of general looking at. So I'm curious. I'm just curious.
Yeah, I think some easier is when I show you the map. You have like a Proterozoic inheritance here, and you have really Archean Craton nearby. But we are thinking here you are more of a Proterozoic inheritance for the subcontinental mantle. Cool. Because we are here, so really in the line of the Proterozoic inheritance.
Trend.
Yes.
Yeah. Okay. Yeah. That makes sense.